Module 2 will be focusing on exploratory data analysis, one form of descriptive analytics. Exploratory data analysis is a set of tools you can use to get a look at what is in your data. First, a quick overview. We'll be looking at two ways of describing data. One is to consider the distribution of each variable in terms of its center, spread, and shape. The other is to look at data through the relationships between the variables in your data set, whether through tables, graphs, or numbers. One of the big concerns in the world of communicating data is that we want our communication to be honest. That is, it should help people understand the data, not cover up essential features that they need to know. And one of the best ways to ensure data honesty is to show the data itself, particularly through a carefully chosen graphical presentation. A spreadsheet with thousands or millions of lines is not nearly as informative as a single, well-chosen graphical display of that data. So, when we do exploratory data analysis, three elements will be involved: a graphical display of the data, looking for patterns and anomalies, and using numerical summaries to describe specific aspects. While I present these here in what seems to be a step-by-step process, the reality is that we often move back and forth through these steps, with each step informing the others, until we are satisfied that we have a good sense of what is in the data we have. One trait we need to consider when exploring and sharing data is the units involved, and whether those units need to be adjusted in some way. As a very simple example, if we're presenting international sales, we need to decide which currency we're going to use. Does it make sense to communicate this data in the currency in which sales occurred, or does it make more sense to convert them to the currency of the headquarters? In making such decisions, we naturally need to think about the questions being asked and transform as appropriate. Similarly, when we are the consumers of data in data presentations, we need to think about the decisions the presenter has made and why they presented the data the way they did, and whether some kind of adjustment might make sense. For example, should we consider a level change, like saying we earned $5 billion more than last year, or a percentage change? Should we look at the total, or at some kind of per capita measure? Should we consider the count, or the count as a proportion of the total? None of these has obvious right answers, since the answer will depend on the question. For each question, think through these options and which is most directly connected to the question being asked. Now let's turn to how we can display data graphically. We'll look at, first, univariate visualizations. These visualizations allow us to communicate the content of data related to a single variable. For categorical or ordinal data, we have two main options: a pie chart and a bar chart, which can be presented either as horizontal or vertical bars. For quantitative data, we can use histograms, frequency polygons, box and whisker plots, and time plots. When considering bar charts versus pie charts, bar charts are usually preferred if we want to give a clear impression of the data. The reason for this is that in a pie chart, human beings estimate the area of the slice based on a rough estimate of the internal angle of the slice. And honestly, that's really hard to do with precision. So at a glance here, it's pretty obvious that dogs are the biggest category and that not quite half of the responses said dogs. Yet the precise number is hard to tell from the chart alone, and how that relates to cats, more than it just being more, is hard to say. On the other hand, bar charts depend on our ability to estimate length at a glance, which is something we're much better at as human beings. So at a glance, it's clear that dogs are more than cats, but not twice as much, even for someone who doesn't want to do the exact division to show it. To prove this, meanwhile, at a glance, we can easily see from the bar chart that more than twice as many people chose fish versus hermit crabs. While we could guess that maybe from the pie chart, it's not nearly as obvious to most people. Here we compare a histogram and a frequency polygon. The two are quite similar in that each divides quantitative data into bins and then reports the frequency of data in that bin. So in this case, about 40 observations are between 6 and 8, as shown by the height of the bar in the histogram and the height of the line in the frequency polygon. Which you prefer is really up to you. I think it's generally safe to say that the histogram makes it a bit more intuitive to compare how many observations are in each bin with each other, while the frequency polygon emphasizes the overall shape of the distribution. One thing to keep in mind when you make either of these, the number of bins and their size is a decision that you as the analyst have to make. Here, there is no hard and fast rule, just the guideline that you want to use a number that makes it easy for people to get the information they need at a glance. As a note, the automatic choices you might find in Excel, for example, are generally not great, but also not far off. Excel has a tendency to give ranges that are just weird for a human being, like 1.725 to 3.428, so we often have to modify what is given to us to make it suitable for human consumption. Having seen a histogram and frequency polygon, I want to introduce a few common distributions that are used in statistics. First, the uniform distribution. This is a flat distribution that gives equal probability to every value within a range. In Excel, the RAND function uses the standard uniform distribution. It produces a number between 0 and 1, so it's a decimal, with each result having equal probability. So zero point 0.5, for example, is just as likely as 0.05 and 0.95. This distribution is rarely seen in reality outside of the rolls of fair dice and things like that, where each side would be equally likely, but it does serve as a good intuitive benchmark for most people. The second distribution is the binomial distribution. It looks at the question of how often a particular event will happen given a number of times in which it might happen, and a particular probability of it happening each time. So this can answer questions like how many coin flips will come up heads if I flip a fair coin 10 times, or what the probability is of rolling a total of 7 on 2 fair standard 6-sided dice. The third distribution is Poisson, what I call the call center distribution. Here the question is how often an event will happen in a fixed time frame or a fixed location. So if you look at the distribution of phone calls a call center receives each hour, it tends to have this distribution, as does the number of trees per acre over a large area. The fourth distribution is probably the most important, and we'll be using it a lot this semester. It is the normal distribution, and as the name implies, it appears pretty frequently. This distribution tends to show up whenever there's an adding up process with some level of randomness involved. So test scores, which are the total score of scores on a number of individual questions, tend to be approximately normally distributed, as does height or weight. In fact, there's a tendency for both binomial and Poisson distributions to tend toward normality as the number of observations increases. So let's take a look. This graph shows 3 bell curves. These bell curves are what we call probability distribution functions. To find the probability of falling within a particular range with one of these, you would take the area under the curve for that range. So here, if you want to know the probability of flipping between 4 and 6 heads, you take the area under the curve from the value of 4 to the value of 6. For our purposes, we can think of these as very similar to a frequency polygon. A higher curve tells us that values around that level tend to be more frequently encountered. These 3 curves show the distribution for the number of heads flipped out of 10 for the blue line, 20 for the orange line, and 30 for the gray line flips. But I did do some smoothing here. The point I want to make here is that the shape is basically bell-shaped and basically symmetrical. That is, if you look on either side of the peak, the distribution looks basically identical. This is typical of a normal distribution, and sure enough, the 30 coin flip case is basically indistinguishable from a normal distribution, even though this one is technically binomial. This shows the Poisson distribution, again with some smoothing, for the amount of mail received per day for various possible average amounts. The blue line is for if the average is 1 piece of mail per day. Notice that here the distribution isn't at all symmetrical. There's a pretty strong probability of either getting no mail or just receiving 1 piece, but once the number of pieces gets up to 2, the probability is much, much less. So to the left of the peak, we have a very high value, but to the right of the peak, It's the opposite, right? We get a really steep drop, but on the other hand, we have this tail that lingers, which we don't see right on the left. However, if we move from an average rate of 1 to an average rate of 5, as shown in kind of the dark orange line here, there's a much greater degree of symmetry, though the left of the peak and the right of it are still not mirror images. We have a much longer tail and a much more gradual slope, in this case, to the right than we have on the left. However, if we make the average rate something like a 10 or 15, then the distribution starts to look more like a normal bell curve, the peak in the middle with the left being symmetrical with the right. Put another way, as the average rate of receiving mail increases, this distribution becomes more and more like the normal distribution. Finally, this is the standard normal distribution, which has a mean of 0 and a standard deviation of 1. The peak in the center indicates that values near the mean are much more common than values out on the edges. In fact, finding values more than 3 or 3.5 standard deviations away from the mean is extremely rare. We'll be revisiting the normal distribution here shortly. Another way of displaying quantitative data is through a box and whisker plot. This plot divided the data into 4 quartiles, each of which contains the same number of observations. The range of the top 25% is shown by the top whisker, and the bottom 25% by the bottom whisker. The box in between shows the middle 50% of the data, which is divided into quartiles by the center line, which indicates the median. This type of chart also typically has some indicator for the mean. In this case, it appears as an X. Some programs, including Excel, will identify likely outliers, that is, data that falls far outside most of the data based on some criterion, and show these as dots that rest above or below the top or bottom whisker. Box and whisker plots are good at telling us at a glance where most of the data lies and the range that all the data lies in. One of the most familiar data visualizations to most people is the time plot. This shows how a particular variable has evolved over time. So, time is on the horizontal axis, and the value of interest is on the vertical. While the previous visualizations focus on the distribution of data points, the time plot focuses on the evolution of that variable across time. Thus, the previous visualizations are good if you want to know what values or ranges of values are more or less common for your variable. A time plot excels at providing you a picture of how your variable moves. For numerical summaries, there are a number of options we can use. One option, which we've already discussed in the previous module, is a frequency table, which simply lists out how many observations belong to a particular category, whether that be a category for a categorical variable, like the color of an M&M, or the range that a numerical value falls within. A frequency table allows us to get a picture of the entire distribution, but in a numerical form. Numerical summaries can also describe 3 main traits of the data. First, the center, as measured by mean, median, or mode. Second, the spread of the data. 2 standard ways of doing this are the standard deviation and the variance, which is simply the square of the standard deviation. In addition, we could consider the range and the interquartile range. Finally, we can consider the shape of the data. Is it symmetric or skewed one way or another? And does it have excess kurtosis? Put another way, how thick are the tails relative to the center and middle ranges? Finally, what is the number of modes? Many distributions have a single mode, but some have multiple modes. Let's look at each of these in turn. First, consider the center of the data as measured by mean, median, or mode. The mean of the data is what we typically call the average, the total sum divided by the number of observations. For notation, we show the mean of a population by the lower case of the Greek letter mu, which looks a bit like a U but with a tail on the left. For a sample mean, we use the letter x with a bar above it. In spoken terms, we call this x bar. Importantly, the mean only exists for interval and rational data. It doesn't make sense to add together ordinal data, even if it's stated numerically, and adding categorical data is clearly impossible. While red plus blue may make purple, that's a fact for art class, not for statistics. The median is the middle value. that line that appears in the center of the box and whisker plot. It is defined by having 50% of the data having a value at least that high and 50% having a value at least that low. Interval and rational data have a median, as does ordinal data, even if it's expressed in word terms. Finally, the mode is the most common category, either for a specific value or a range of values. On a histogram or a bar chart, it's the highest bar. All data may have a mode. When considering spread, there are a number of ways to measure spread. One is to use the range, that's the maximum value minus the minimum value. Another is the interquartile range, or IQR for short. This subtracts the 75th percentile from the 25th percentile. You can see these most easily on box and whisker plots. The interquartile range is just the height of the box, part of the box and whisker. Another common measure is variance and standard deviation. The variance is the average of the squared distances between observations and the mean. The standard deviation is the square root of that, so it gives a rough idea of how far from average observations are, on average. Standard deviation for a population is denoted by the lowercase sigma, which looks a bit like a cursive O, and for a sample, the letter S is used. For variance, you just add the superscript 2 to these to show that they're squared. Now, one way of identifying outliers is to take the size of the interquartile range and multiply it by 1.5. Then any point that is that far from the interquartile range is considered an outlier. The one concern, which I just brought up, and we'll look at more in the next couple slides, is outliers. Now, outliers are observations with values that are remarkably different from the other observations we have. Now, sometimes outliers are true, that is, they reflect real data. While there are very few billionaires, they do in fact exist. However, some outliers are signs of an error in the data collection process. For example, if someone claims to be 608 inches tall, that's over 50 feet, odds are that a typo was involved. In either case, though, if we have a small sample, then outliers can create inaccuracies, which we'll discuss later, so it's a good idea to identify them so we can decide if we should correct them. Now, one method for identifying outliers is to use intuition, combined with a sorted list of the data or a visualization, like a histogram. These allow us to identify if there are a data point or two that are far removed from the other data points, which would suggest they're outliers. Another method is to use z-scores. The z-score for a data point is the distance from that data point to the mean, and then dividing that by the standard deviation. So if the z-score is greater than 3 once you ignore any minus signs, then this is a likely outlier, or at the very least it's worth investigating. A last method is the interquartile range method. For this, you calculate the interquartile range and identify any point that is at least 1.5 times that away from the interquartile range as an outlier. This one gets a little bit confusing perhaps. Let's look at an example. If the 25th percentile is 10, 75th percentile is 16, then the interquartile range is 16 minus 10, or 6. Multiply that 6 by 1.5 and that gets us 9. So any observation that is more than 9 away from the 10 to 16 range would be considered an outlier. So in this case, more than 9 away from 10, that would bring us down to 1. So anything less than 1 or more than 16 plus 9, it's 25. So anything outside of that 1 to 25 range would be considered an outlier using this method. When describing the shape of a distribution, we typically encounter two traits: skewness and kurtosis. For skewness, a negative number indicates what we call left skewness. That is, that most of the data has fairly high values, but that there are some data points that are far below the mean. As a result, the mean tends to be less than the median for these distributions, since the low value drags down the mean. But it has less effect on the median. A positive number for skewness is the opposite. That is, we have positive skewness, or right skewness. That means we have a distribution where most values are relatively low, but some small handful are quite high, resulting in a mean that is above the median. Kurtosis is all about the thickness of the tails relative to a normal distribution's tails. If kurtosis is negative, then you have a thin-tailed distribution, What that means is that most of the data stays fairly close to the mean and very, very little is further away. Meanwhile, positive kurtosis indicates thick tails, so data tends to be either extremely close to the mean or extremely far away in those distributions. We also call these platykurtic and leptokurtic. More on what can cause these particular shapes later. So there are a lot of options. Which is the best? Should we prefer to use a mean or a median as a measure of center? A standard deviation or an interquartile range as a standard of spread? To figure this out, we have to consider the traits of each of those options and how they interact with the specific data that we might have. So here are some considerations. The mean and standard deviation are sensitive to outliers. Since outliers are by their very nature far away from the rest of the data, they would tend to have a big impact on standard deviation. They would drive it up. They also, though, would push the mean in the direction in which they fall, since they also have a significant impact on the total, and that total is something we use to calculate the mean. Meanwhile, median and interquartile range are much less sensitive to outliers. Since the median is the middle value, it doesn't really matter how far from that middle value the extreme values are. The middle's the middle, regardless. The interquartile range similarly is going to ignore both the bottom 25% and the top 25% of the data. So it's not going to be as affected by the outliers, will almost certainly fall in that range. However, by effectively ignoring the specific values of a lot of the data, these measures are considered less efficient. That is, they don't make full use of the data that we have. Another way to think of this is that the mean and the median tell different stories when data is skewed. For example, income data has a very strong right skew. That is, there are a few households that have really, really high incomes. These are going to drive up the mean income. So the median will give us a more accurate picture of how most households are doing. However, if we're considering whether, say, society as a whole can afford something, then the mean income is a better measure, since it would account for the fact that there is some enormous wealth out there that might possibly be able to be used for whatever this expense happens to be. Similarly, standard deviation and interquartile range are going to tell different stories if the data has very thick tails. In this case, standard deviation will tend to be much higher and will capture that spread that is created by those extremes. Meanwhile, the interquartile range does a better job of telling us how close most observations are to each other. Some additional considerations. When trying to project a total, the mean is typically quite helpful. Since the mean is the total divided by the number of observations in the sample, we can project a total for the population by just taking our sample mean and multiplying by the number of observations we expect in the population as a whole. However, when we're not interested in the total, but in what experience we might call typical, then the median tends to be quite useful. Also, there are times when the entire distribution is really the most useful thing to know. If I'm managing a clothing line, simply knowing the median height isn't particularly useful. People of all heights want to buy clothes, so I need to know roughly how many people there are of each height. That requires information about the entirety of the distribution, not just a number or two about the center and spread. Now, just a note about the interpretation of spread. Spread gives you a sense of how similar the data observations within the data are. For example, if every data point is exactly the same, the standard deviation would be calculated to be 0. Similarly, the interquartile range, if that's 0, that tells us that the middle half of the data, at least, has exactly the same value. Now, for a normal distribution, we have what we would call the 68, 95, 99.7 rule. Yeah, statisticians aren't very good at coming up with creative names, but you can remember the rule, then its interpretation is pretty easy. 68% of the data falls within one standard deviation of the mean in a normal distribution. Meanwhile, 95% falls within 2 standard deviations, and 99.7% falls within 3. That would be why one of the outlier rules says that anything more than 3 standard deviations outside the mean is probably an outlier. That's simply because we usually expect only about 0.3% of the data to be that far away from the mean. Sometimes it is useful to scale the standard deviation by the mean. As a number, standard deviation doesn't necessarily have a very strong meaning, but when we divide it by the mean of our data, then we have a value that's relative to something else that's based on our data. Now this number, the standard deviation divided by the mean, we call the coefficient of variation. And it can be used if we want to judge, for example, whether height or income shows a greater degree of variation in a particular society. Since this coefficient of variation doesn't depend on the underlying units used for measurement. As you make choices about spread, again, I want to remind you of the trade-offs involved. Standard deviation and variance use more information, so we consider them efficient because they don't ignore the value of any of our data points. However, that also makes them sensitive to outliers. At the same time, interquartile range uses less information, so it's less efficient, but it's also more robust against outliers. And finally, the range, that is the maximum minus the minimum, is a worst of both worlds. It only uses 2 data points, so it's extremely inefficient, and these 2 data points are also the ones that are most likely to be outliers if we have any. So it will be heavily influenced anytime you have an outlier. As a result, we generally don't actually use range unless we have some really specific reason that we'd need to know that trait. Because the normal distribution is so common, let's spend a little more time examining some of its traits and how we can see deviations from them. First, for the normal distribution, the mean, median, and mode are all the same. That is, the peak appears in the exact middle of the distribution. Second, the normal distribution is symmetric. The left side of the peak is a mirror image of the right. If you calculate skewness, you'll get a 0. Third, the amount of data you find within each range is known. 68% of data falls within 1 standard deviation of the mean, 95% within 2 standard deviations, and 99.7% within 3 standard deviations. If you use Excel formulas to calculate kurtosis, they report that excess kurtosis is 0. Now, it's important to remember, these are ideals. In reality, even normally distributed data may not align with these exactly, so we have to have a little tolerance around these values. The normal distribution, apart from being very common, is also used as a benchmark. In short, we start by assuming that data is normal, and then look for possible evidence that it isn't. Very important here, what makes the distribution normal is not the mean or the standard deviation. Rather, it's how the data is distributed around the mean. That 68, 95, 99.7 rule and symmetry are key. However, that said, real data normally doesn't look totally clean, so we'll probably need to ignore minor deviations. What exactly that means we'll get to soon, but let's turn to the kinds of deviations from normality you may see. Deviation is skewness. A distribution is considered skewed if it has extreme values on one side of the distribution, but not on the other. A common cause of this is if there's a meaningful limit on one side, but not on the other. For example, household wealth is right skewed. That is, it has some extremely high values, but it lacks extreme low values when we compare it to the mean. The reason for this is that there's a practical limit to wealth, right around 0, but there isn't really a practical upper limit. As a result, we have many people with a net worth right around 0, but a small handful with billions upon billions of dollars of wealth. A quick point in terms of terminology. The direction of skew is determined by the direction of the outliers, not the direction of most of the data. So if most data is low, but there are a few high values, the data would be considered right skewed. If most is high, but there are a few unusually low values, that's left skewed. There is some disagreement about what level of skewness can be tolerated and have a distribution still be approximately normal, but if your skewness has a magnitude of 1 or less, then the data is quite close to normal, and if it's less than 3 in magnitude, then some people would still consider that to be tolerably close to normal. Second deviation from normality we may see is in kurtosis. This would be a deviation from the 68, 95, 99.7 rule. There are two deviations that can happen. One is that a distribution can be leptokurtic. These distributions tend to have a very strong central peak and then very fat, long tails, so that overall you actually have less than 68% of the data within one standard deviation of the mean. The opposite of this is platykurtic distributions, where extreme values are extremely rare, so that more than 98% of the data falls within one standard deviation of the mean. Often, platykurtosis happens when there are limits on both sides that prevent extreme values from happening. For example, the standard uniform distribution is limited at the top by 1 and at the bottom by 0, so it would be considered platykurtic. Leptokurtic distributions may indicate outliers are very common both on the high and on the low end. Rather like with skewness, there's some disagreement about how far from normal kurtosis can go and still be normal. If the magnitude is less than 1, then we're pretty close to normal, and some people suggest a kurtosis even as high as 10 or negative 10 could still be close enough for us to consider the data normal, barring any other concerns. Here's an application of kurtosis from a few years ago. Nassim Taleb observed that in financial returns there are two deviations from normality. First is a left skew. That is, there are extreme negative values, but basically no extreme positive values when you compare to the mean. Second, the left tail is fairly thick compared to the right tail, which really doesn't exist. You can see that in the histogram here. A histogram, is a bar graph for quantitative data, and it shows how many observations fit in that particular range. It's a common way of showing the distribution of quantitative data. So here we can see that most of the time the Wilshire 5000 returns between 5% and 35%. However, it never returns above 35%, so there is no right tail outside that range. Meanwhile, there is a left tail showing unusually low returns, including some even worse than losing 35%. As he says, the market is usually good, but when it gets bad, it gets very bad. The third deviation from normality is multimodality. That is, when the distribution has two or more modes, that is, peaks in the distribution, even if they may not be true modes in the strictest sense. A normal distribution should have one clear peak, one clear mode, but sometimes you'll observe a distribution that has two or three. Often this multimodality, if we expect a normality for the type of data we're looking at, would indicate that we have wrongly combined multiple data sets. For example, consider this histogram for heights in inches. Take a second to see how many modes it has. So pause the video, continue when you think you have the answer. To me, it looks like this distribution has two modes. That is, it is bimodal. One mode is in the 34.5 to 35.5 inch range. The other is in the 39.5 to 41.5 inch range. I consider the drop at that 40.5 to just be a blip in this data. So why did this happen? Well, take a second to pause the video again, see if you can figure it out. All right, if you're looking at these heights, you might realize they feel a bit short. This isn't for adults. Instead, this is for two different ages that were combined. I believe it was 4-year-olds and 6-year-olds, if I recall correctly. Now take a look at this histogram. This histogram is for miles driven. Take a second to look at this, decide what kind of distribution this is based on what was described before, and whether this makes sense for this particular data. Pause the video and then resume when you're ready. If you're thinking this looks like a uniform distribution, then you're right. Uniform distributions are basically flat, which seems to be the case here. There certainly is nothing resembling the bell shape that we would see in a normal distribution. So, given that this data is supposed to be for the number of miles driven over some period of time for a car, this data is highly suspicious. After all, we expect that most people will be average drivers, driving for commutes, grocery store trips, the occasional vacation. Now, there will be a small number of people who own cars but very rarely drive them. Here I think of, say, older ladies that only drive to church, but basically not at all otherwise. On the opposite end, we would expect for there to be some people who drive way more than average. Maybe they love road trips or have unusually long commutes or something like that. However, we'd expect the extremes would be less common than the average. However, that's not what this data shows. The problem here is that this data was fabricated. Probably using some kind of random number generator like rand_between in Excel, which returns numbers between two values with an equal probability for each. It turns out this was a big problem because this fabricated data was used in a scientific study by behavioral economist Dan Ariely. He says the data was provided to him by an insurance company, which may be true, but the moral of this story is that we should always check our data. A little bit of exploratory data analysis, in this case a single histogram, should have caused a bit of caution before moving ahead with using this data. So just a reminder, most data we deal with will be normally distributed or pretty close to it, particularly when observations are the result of adding up or averaging across some other random distribution. For example, while a single six-sided die roll has a uniform distribution, the sum of 30 of these rolls is extremely close to a normal distribution. In fact, even adding up three die rolls will get us quite close. Now, there is a special form of the normal distribution that we call the standard normal distribution. This is the normal distribution that has a mean of 0 and a standard deviation of 1. Any normal distribution can be converted to this by calculating what we call the z-score for each data point. The z-score is simply the original value, which I denote in this formula by x, then you subtract the mean, here denoted as mu, and then divide that by the standard deviation sigma. This transformation takes the data from its raw value to how many standard deviations it is from the mean of the data, and also in which direction. Negative numbers will be for those observations that fall below the mean, positive for those above. So a z-score of 1.5, for example, indicates that the observation is 1.5 standard deviations above the mean value in the data. Now, everything we've done so far is about the distributions of a single variable. Now let's turn to relationships between variables. So first, let's get this out of the way. Correlation does not imply causation. That is, sometimes we find that two variables are statistically related, but there's no causal connection between the two. These spurious correlations can cause problems if we just start looking for statistical connections at random. TylerVigan.com has a great collection of these, and I recommend checking that out sometime. That said, when we talk about relationships, we will often divide the variables into two types: explanatory or independent variables, which are used to explain the other, and response or dependent variables. Now, in an ideal world, explanatory variables are the cause and response is the effect. So if we have that knowledge, we can set things up this way. But such knowledge is not really necessary. We just have to be cautious if we don't already know about causation. So, when we consider two variables, there are 4 different possible combinations we may be dealing with, and which combination we have changes what type of visualization we'd want to use. So first, we may have a categorical explanatory variable and a categorical response variable. In this case, a two-way table is a great option. A two-way table simply has one category that determines the rows, and the other determines the columns. And the entries in the table just tell you how many observations fall into each combination of those traits. Excel can create these using the pivot tables option. Second, we may have one of the variables be categorical and the other quantitative. In this case, we'd use side-by-side box plots, with a box plot for each category, and the quantitative variable is used to determine the shape of that box and whisker plot. Third, if both explanatory and response variables are quantitative, then we could use a scatter plot. So let's start with side-by-side box plots. A side-by-side box plot allows us to see how the data for each category compares with other categories. For example, if there's a lot of overlap in the boxes, that tells us that most of the data is pretty similar. However, if the boxes do not overlap at all, that tells us that there is no overlap in the middle half of values for the quantitative variable for one category versus another category. Here's an example. Test 1 scores are in the blue box plot, Test 2 in the red. Here we can see that Test 2 seems to have been slightly easier. In fact, the median of the second test seems to have been about as good as the 75th percentile for the first test. And in fact, even the worst performing student on test 2 did over 10 points better than the worst performing student on test 1. Meanwhile, if we look at the high end, the best score doesn't seem to have improved very much. Now, scatter plots. A scatter plot shows the relationship between two variables, the horizontal or x variable, which is usually the independent or explanatory variable, and the vertical or the y variable, usually the response variable. Each point on the scatter plot indicates that there's an observation with that combination of traits. So for example, if the x variable is height and the y variable is weight, and there's a point with at 68 inches, 170 pounds, that would indicate that if we have a person in our sample that has that particular combination of characteristics. We can interpret scatter plots along three traits. First is the direction of the association. Is it positive, with higher values on one axis being associated with higher values on the other? And we would see this in an upward sloping line or curve. Is it negative, which would be a downward slope, would indicate that one variable is high while the other is low, and vice versa. Finally, there might be no association at all. In that case, that scatter plot tends to either look like a cloud or a perfectly flat line. Second, the form of the relationship can be seen. Is it linear, that it appears to be nearly in a straight line, or is it curved in some way? For example, it might be exponential with an increasing slope, or quadratic with a U-shape. Finally, the strength of the relationship, that is, how close are the points to a line or a curve that would describe the typical relationship. If the points fall very close to that line, we'd call the relationship strong. If they're far away, then we'd call it weak. Now, there are times we may want to take a curved relationship and force it to be more linear. One common example is using a logarithm to make an exponential data set look linear. This is typical if we're looking at, say, data points over time, and time is on the horizontal axis. And then we expect the data to have a fairly stable growth rate as a percentage over time. Now, naturally, if you're unsure, you can always just plot the data, check, plot the transformation, check, and make the decision there. So here we have the relationship between income on the horizontal axis and reported happiness on the vertical axis, based on the average income in a country and surveys of people within that country. So take a look at this one, decide if you think the relationship is positive or negative, strong or weak, and linear or nonlinear. Pause and come up with your answer. First, this is pretty clearly a positive relationship. Richer countries report higher levels of average happiness. Now, in terms of strength, this seems moderate. I couldn't draw any reasonable curve or line that all the points would fall on or extremely close to. At the same time, it isn't super weak either. You don't find weird exceptions with extremely happy poor countries or extremely unhappy rich countries. Now, as far as linear versus nonlinear, this looks like it might be linear or very close to it. That is, a straight line wouldn't be an obviously bad way to approximate this relationship. Though it does seem, at least to me, that at the lowest levels of income, there's a steeper relationship than you have at the higher levels. So there might be a little bit of curvature there, with the appropriate curve starts steep, but then would flatten out more as we move from left to right. So it would really be, I think you can make a judgment call on that one. When working with numerical data, the main way that we can numerically describe these connections is through correlation, which can be calculated as shown here. Now don't bother memorizing the formula, please. The point here is that correlation is based on looking at how the values of the two variables compare with their means, and then finding what this average relationship looks like. Now, what does matter? Correlation takes a value between -1 and 1. If the value is close to 0 in an absolute value, that suggests there's no relationship, or more precisely, no linear relationship. Correlation will not find a U or a V-shaped relationship, for example. Now, an absolute value near 1, so 1 or -1, indicates a very strong linear relationship. Now, the exact cutoff between no relationship and very strong, it depends on the field and is usually related to the complexity of the data. So for example, in physics, if you're running an experiment and the data you get, you find a correlation of 0.3, that might be considered really, really low in that context. It's fairly simple data, controlled experiment. At the same time, that same 0.3, if we apply it to social science data that we gather out in society as a whole, that 0.3 might actually be considered quite high in that case. It's a much more complex situation. We'd be more surprised to find a really strong relationship if there aren't these experimental controls. Now, another point, even if we find a strong correlation, whether it's positive or negative, we can't immediately assume causation. Remember, spurious correlations do exist. Now, finally, correlation can be sensitive to outliers. Unfortunately, it's in an unpredictable way. Outliers affect the mean, they affect the standard deviation, and they also affect the correlation itself. So every element that goes into the calculation we saw a slide ago gets affected by outliers. And then because of the interrelationship between these things, it's not obvious whether correlation is going to get overstated or understated when outliers are in the data. So a good practice may be to try calculating correlation twice, once including any outliers and then once excluding them from the data set. That way we know whether they made a difference and what kind of difference they made. One more way to describe a linear relationship between quantitative variables is through regression. What regression does is take a linear relationship and then describe it with algebraic precision. The idea here is to have a formulaic way of turning our intuition or observation of a likely linear relationship into a best fit formula. So here's the basic idea. We assume the underlying reality is that there's a linear relationship between x and y. Put another way, y is equal to some intercept, we'll call it alpha, plus some slope beta times x. But with some other factors, we'll call those epsilon, added into the mix. Now our statistics will give us an estimate of this equation. To find that estimate, what we're going to do is calculate an intercept in our stats equation, that'd be a, and a slope b, that's going to minimize the sum of squared errors. Now put another way, we want to find that linear relationship that does the best job explaining or predicting y, minimizing any errors that we get if we try to use our equation and our x values to predict what those y values are. Here are the formulas. I wouldn't bother memorizing them. The key that I'll point out, notice that the slope is based on the correlation. So a negative correlation will give a negative slope. Positive correlation would give a positive slope. And that's exactly what we want to have happen. Now, how do we interpret all the bits of this equation? First, the intercept tells us what the value of the dependent variable would be if the independent variable had a value of 0. This isn't always meaningful. For example, if we're using height as our independent and weight as our dependent variable, then a height of 0 is pretty meaningless. Nobody is 0 inches tall. The slope tells us that if there's a 1 unit increase in the independent variable, there is on average a b unit increase in the dependent variable. So if we have a slope of 2 in our height-weight regression, with height as the independent variable, that tells us that a 1 inch increase in height is associated with, on average, a 2-pound increase in weight. There's also a statistic called r squared, which tells us how much of the variation in y can be explained by x. It's a measure of the goodness of fit. Finally, Excel also reports something called a t-stat. We'll get more into this when we cover regression in more detail at the end of the course, but if the t-stat is greater than 2 in magnitude, that tends to be what we call statistically significant. More on what that means in a few modules, though. Here's the kind of output you might see from the previous scatter plot. Take a minute, see if you can answer the questions on the screen. I'll go ahead and pause now. Okay, the first question is answered by r squared. So in our data, we can explain 74.58% of the variation in happiness. So while we can't say anything conclusively about money buying happiness, it seems that money is at least associated with it at a reasonable level. If the income was 0, then the happiness score would be 8.78 or so on average, as indicated by the intercept. If a country's household income went up by $10,000, then we'd expect to see an increase in happiness of 10,000 times the income coefficient. An important note here that E minus 0.5 indicates that this line was stated in scientific notation. So this value is not 6.84, rather 6.84 times 10 to the negative fifth power. So you'd have to multiply that by 10,000, and then we'd get something in the neighborhood of 0.684. Now, a few cautions about ordinary least squares, the form of regression we're doing here. First, forecasts are not perfect. They have what we call residuals. One of the options in Excel is to get a residuals plot. Examining that can be revealing. If you find patterns in those residuals, for example, that suggests that there's something predictable that the linear model just isn't catching. This is very common if the relationship is actually curved, like if it's U-shaped or if it's V-shaped. Second, outliers can have big impacts on OLS results, so be careful. And finally, we must keep in mind the possibility of omitted variables. Ordinary least squares doesn't tell us if causation is there, just if there's an association in linear form. So we might falsely identify causation if we move too quickly and without caution. Similarly, we might actually miss true causation if the dependent variable is the result of a complicated process. So just because a simple regression doesn't find a relationship doesn't mean there isn't one at all. So when considering causation, there are a few things to keep in mind. First, in an ideal world, our independent variable does cause the dependent one, in which case the OLS table does a good job showing the relationship between them. But we can also have something called a common response, which happens when there's an omitted variable. This would be a case where something else is causing both our x variable and our y variable. For example, there's a strong correlation between sunburns and ice cream sales. Does it follow that one causes the other? No. Instead, both of them are seasonal, more common during the summer, less common during the winter. That is, what we're finding is a common response to some common cause that wasn't directly part of our study. A third possibility is what we call confounding or multicollinearity. This happens when two variables both influence our dependent variable, but those two variables are themselves very strongly correlated. This makes it extremely difficult to tell which matters and how much. This is the problem with many studies that are trying to figure out if nature or nurture is more important in parenting. Generally, people with similar genes tend to have similar upbringings, so it's very hard to say which it was that mattered. So, how do we get toward causation? Here are a few things that can help. One, particularly strong associations are more suggestive than weak ones. Second, if we consistently find a particular association across different contexts, like in different times or different places or in different samples. Third, if the slope is large given the context, we would call this economic significance. Fourth, if the cause precedes the effect in time. We can sometimes use lagged data to look for this. And finally, I'd suggest most importantly, does the relationship make sense? That is, do we have a sound theory, a story that backs it up? If we can't come up with a reasonable story, then we should have some significant doubts that the association we found actually has causation in it at all. Finish up then. In this module, your Be the Human task is to select visualizations and numerical summaries that make sense in the context, both in terms of the broad choices and the small details, and to interpret whatever your exploration finds, the trends and the deviations from them, practically, given your context. In terms of using the computer, use those to create the summaries and the visualizations. While you can calculate means and standard deviations by hand, there's very little benefit in doing so nowadays. Let the computer do that part. Your job is to know what they mean.